Assalamu alaikum everyone. So we hope that you all are doing well. So today we are going to present our calculus project that is named as Complementary Coffee Cups. Before starting with this presentation, let me introduce myself and my group members. So here I am Arisha, and beside me, my other group members Arwa, Shalin and Batul will also be speaking. So starting with the basic outline that what we will be discussing in this project is that under what conditions the two cups are called as complementary cups, and under what conditions the two such cups will hold same amount of coffee, how is the volume of such cups are computed using two different approaches or methods. One of them is disk method and another is through Pappus theorem. Furthermore, we will solve for h, that is height for cups, and an equation for f of y. And in the last, we also be discussing about when a cup would be complementary to itself. Also, the inspiration behind this project is that if you have two such cups and you wonder that which cup would hold more amount of coffee, then of course you could fill one cup with water and pour into one another and do comparison for which holds more amount. But we could also go for some more mathematical approach, and here it is. Initially, before adding at first we need to understand that what do we basically mean by complementary coffee. So such cups which have some specific profile curves that fit into one another or fit in together or are considered as complementary coffee cups. And these cups represent solids of revolution and are of same height. In the pictorial representation and the graphical representation shown below, we can see that the white cup has its middle part extended outwards, and another black cup has its middle part shrinked inward. Also, the 3D graphical representation on the right side shows that the complementary coffee cups are basically those cups which are arising from parabola and is made up of multiple parabolas. And in the context of the case shown in these pictures, we see that cups represent surfaces of revolution and coffee within these cups can be taken as volume of revolution. So moving forward to our task. We have a task one in which that we are supposed to find the value of k such that the two cups hold the same amount of coffee. In this case, our assumption is that the volume for these two cups are assumed to be equivalent, and the goal is for finding the value of k such that cup A is formed by rotating the curve or parabola around the y-axis, and the cup B is formed by rotating the same curve about the line x is equals to k. So as shown previously in the graphical representation, we can see that we have a line x is equals to k, which is parallel to y-axis, and cup B is formed basically by rotating around line x is equals to k, and cup A is formed by rotating the parabola around y-axis. Assumption made in order to solve for k are that the cups are handleless and the cups are assumed to have no thickness. So as previously discussed that we will be looking for two different approaches, that is disk method and Pappus theorem. So at first we will go through disk method, which is also known as disk integration. And in this method, the volume of full solid of revolution is computed or figured out by summing the volumes of thin cylindrical disks. So coming to our main goal or core, that is solving for k using disk method, referring to the diagram I have shown on the right, we have a red parabola, a red curve, and a purple and some purple curves. So red parabola represents our basically cup A, and purple curves represents cup B. So the radius for cup A, symbolized as RA, is basically a distance between the vertical y-axis and the vertex of red parabola, and RB is basically a radius which is symbolized as RB, and is the difference between the distance x is equals to k and f of y. That is written here on the left, and the height for both of them is h. That is, we have chosen a specific interval on y-axis from 0 to h. So experimental volume, as we said, that this method is based upon dividing a full solid of revolution into minimal or into thin, tiny cylindrical disks. We know that the volume for a cylindrical disk is pi r square h. And the context of this case, we know that we we have our r as f of y and our h is delta y. That signifies the minimal change or the smaller change on the interval of y. So referring to the concept of our Riemann sums, we know that if a volume of one disk is computed as following, then the sum of volumes will represent the volume of the entire solid of revolution that is signified by this summation. And now definite integral as the limit of Riemann sum, we have this final expression for the volume. Now, by the second framework definition, we know that V1 is equals to V2 for volume of cup A is equal to volume of cup B. We see that by some mathematical computation or manipulation, by cancelling out pi, by expanding the whole square formula, we ended up on cancelling out same integrals. And then we get this. From here, we integrated the rest. We figured the decided values, decided upper limits and lower limits, and in the end, we got to the two values of k, that is x is equals to 0 and x is equals to as following shown on your screen. So x is equal to 0, that means that x is equals to k and x is equals to 0 then. So x is equal to 0 signifies or notifies the y-axis, and in the picture shown before, we have assumed that x is equals to k is a line which is parallel to y-axis. So that is why we are going to ignore k is equal to 0, and we will take into account this value of k. Furthermore, I would hand over the command to Shalan to discuss furthermore tasks, and let's see what do we have more for you.
Okay, so for now, task 2, what we have to do is that we have to look into problem 1 and figure out what the areas of both cups say about each other, or what is the relation between the areas of both cups. So from problem 1, what we noted is that for a certain value of k, the volumes of both cups are equal to each other. So what about the areas of these two cups? So keeping our equations in mind, what we found is that our volumes are equal and we had these equations with us. So following the same procedure as we did in problem 1, we have these integrals equal to each other that show the volumes of both cups respectively. And cancelling pi from both sides, we get this equation, and expanding furthermore and cancelling out similar integrals. Now we have a simplified form of our equation, which is this. Now what we do is that we take out the factor k from this integral and we divide this k on both sides to get rid of this k. But before dividing it on both sides, what we note from problem 1 is that our k is greater than 0. We will not look into the value of k when it is equals to 0. So keeping that in mind, we have divided k on both sides, and furthermore splitting this integral, we have this equation, that is integral k dy is equals to 2 times integral f of dy. Now, what we have to note here is that what does this equation says about the areas of these two cups? So we know that our limits for the function is 0 till h on the y-axis, and computing this limits on the left-hand side of our equation, what we get is that k times h is equals to 2 times integral f of y dy. Now, referring back to the figure again, we can see that k times h is the area enclosed by this rectangle. So the area enclosed by this rectangle is a1 plus a2. So we can write it as a1 plus a2 is equals to k times h. And what we can also note from here is that our curve f of y, when we integrate it, we get the area a1, which is half the area of cup A. So doubling it, we get a1 plus a2 is equals to twice integral f of y dy, which is the area of the cup A. So now what we do here is that Since we know that these both equations are equal to each other, and we have just found that a1 plus a2 represents k times h, and twice the integral f of y dy represents a1 plus a1. So we can cancel out a1 from both sides, and what we get here is that a2 is equals to a1, or we can write it as a1 is equals to a2. So our conclusion from problem 2 is that we can say that the areas of two complementary cups are equal under a condition when their volumes are also equal. So we can write it as volume V1 is equals to V2, which is biconditional A1 is equals to A2. So now I like Arva to take over.
Okay, so we will discuss an alternative way, which is the Pappus' theorem. The statement of the Pappus' theorem is that let D be a region in the plane and let L be a line in the plane of D. If L does not meet D, then the volume of the solid generated when D is rotated around the line L is given by V is equals to AP, where A is the area of the region D and P is the perimeter, or we can say the circumference of the circle that is formed by the centroid of the region D as it revolves around the line L. Now, if we consider the problem at hand and we apply Pappus' theorem on this problem, we can see that there is this region A1, which we can consider as a region D, and the line that around which it revolves is y-axis. And then there is another region which is A2, and the line for it is the line x is equal to k, around which it revolves. So let's apply Pappus' theorem on the first region A1. Here we can see that from the Pappus' theorem it is V1 is equals to A1 into P1. A1 is simply the area under the curve given by the integral of Fy, and P1 is equals to the circumference, which is 2 pi r1. Now here r1 is the distance of the centroid of the region from the y-axis, which is given by the x-coordinate of the centroid. Now, if you want to find the position of centroid of any region, the formula for finding the x-coordinate of the centroid is given by the total movement in the x direction, or the total movement across the y-axis over the total mass. Now, for region A1, we divide the whole region into small strips, and the centroid of each strip can be given by xc, yc, and the mass of each strip that is concentrated toward the center of the strip is given by delta m. So in here, the equation simply becomes of the x-coordinate of the centroid, the sum of all the x-coordinate of each of the strips. Now, if here we see delta m is actually the density into area, and xc is actually, if we consider the strip to be very thin, then xc is the distance between the y-axis and the curve, which is fy over 2. It's because the strip is very thin. So we substitute these values and cut raw from above and bottom, and then we substitute the value of area of each strip, which is simply given. So we get this equation for the coordinate x-coordinate of the centroid. We put this we get this value of parameter. We substitute A1 and P1 into the volume equation. We get the volume, which is pi into the integral of Fy squared, which is exactly the same value that we achieved in the problem 1. So this is how it verifies our problem 1. Moving on, we do the same exercise for region A2, and we see that V2 is equals to A2 into P2. And A2 is obviously area under the curve k minus Fy, and P2 is 2 pi r2, where again r2 is the distance of the centroid from the y-axis, which is actually the x-coordinate of the centroid. Now finding the centroid, for finding the centroids, we again divide the whole region into small rectangles and we substitute the value of xc, which is k minus fy over 2, the exact center of each strip. Then we substitute all these values. We substitute the value of delta A, which is k minus fy, which is the length of the strip, and delta y, which is the breadth of the strip. And then we get this value of the x coordinate of the centroid. We substitute this value of x coordinate of the centroid in the equation of the perimeter, and then we get this equation of the perimeter. We simply substitute this value of the equation of the perimeter and area into the equation of volume, and we get this value of volume, which is again the same volume we found in the problem 1. And if we equate these two, v1 is equals to v2, we'll get the similar value of k. So this is how Pappus's theorem is another way of finding volume. Now I'll hand over this to
So can you all see my screen?
Yes.
Okay, so now we have the equations for k, v1 and v2. So if we can suppose a value for the height and an equation for x is equals to f of y, we can visualize our results. So after playing around with many different values, we decided that the height should be 10 and the equation should be x is equals to 5 minus 0.04 into y minus 5 square. How did we come at this equation? We use the general equation of a parabola. So if you look at the graph on the right, it resembles the graph we were given in the problem statement. Now to calculate the volumes, we need to calculate the value of k, which was the axis of rotation for the second cup. To calculate the value of k, we need to substitute h and the equation in the equation of k that was derived in task 1. So doing so, we find out that k is equal to 28 over 3. We will leave it in its fractional form for the sake of accuracy. Now, we will substitute our values in the equations of the volume which were derived in task 1 and task 3. Doing so, we find out that V1 is equal to 656 pi over 3. Similarly, V2. Can you guys see my screen?
yeah, we can.
Okay. Similarly, the volume of the second cup also comes out to be 656 pi over 3, which proves our initial suppositions. So now some food for thought, more like some coffee for thought. We found out that a cup can be complementary to another cup. But can a cup be complementary to its own self too? Yes, a cup or a solid of revolution can be complementary to its own self if it obeys the property that is written there. So first of all, we look at what A and B are here. So A is the lower limit and B is the upper limit. So how did we arrive at this theorem? So intuitively, for a cup to be complementary to its own self, it needs to have rotational symmetry about the center of the rectangle that encloses both the cups. So that the center, we are naming it as C. So if we translate our equation such that this P becomes its origin, we get the equation g of y. So for a function to have rotational symmetry about its origin, it needs to be an odd function. And as we know, for odd functions, g of y is equals to minus g of minus y. The value of g of y in this representation. Doing so, we arrive at our theorem. This shows that the average of two certain x values gives us half of the distance from the axis of rotation. This brings us to the end of our presentation. Thank you, and the floor is now open for questions.